Okay, so for this mechanical efficiency calculation stuff here, again, we need to look at the amount of power that we're getting out of the system compared to the amount of power that we're putting into the system. All right, so for this situation, what are our formulas here? What formulas do we need to use? Nico? Okay, so we know we need to use work. What is work equal to? Force times distance is correct. What else do we need? Power, right? P in. What is the formula for P in? Current times voltage, right? That's what we're putting into that system. Remember, we put so much voltage, so much current. That's what powered that winch to move. Then what did we get out of it? What was our P out equal to? Yeah, work over time. And notice I did a small t. What's a big T stand for? Not torque, but temperature, right? So big T is temperature, okay? The last thing we need to know here is what our efficiency calculation is. And for us, our efficiency, we're always looking at what we get out of the system compared to what we put into the system. So it's always out over in. You know, if you go back to our simple machines, we had the AMA versus the IMA. Okay, so AMA over IMA for efficiency. Okay, so up here is all the information we need. We just have to do a couple of calculations in order to figure this out. So looking from left to right, I can see I have a newtons times meters, which is a force times distance, so it's work. So for the first one here, what I'll do is figure out, okay, I know that I have 40 times 20, right, that's the work, which equals 800. And what would our answer be for that? 800 what? Joules, right? Okay, so for the second one, we have 90 times 20, which is 1,800 joules. And for the third one, we have 215 times 20, which is, say again, 4,300, correct? Okay. So that gives us the work that's done for each of those scenarios. But we also have to figure out what's really our power out here. So we just need to divide our work by the amount of time it took. So I'm just grabbing the information from the chart above where we had 8 seconds for the first one, 10 for the second, 14 for the third. So 18 by 10, 14. Okay. So if you did the math here, 800 divided by 8 should be pretty easy. Put the units here, sorry. We get 100. What are our units for power? What are our units for power? Watts, right? Watts. Okay. So what we solved for right here was P out, right? P out, work over time. Okay. Well, what is 1,800 divided by 10? That's a pretty easy calculation. And the last one's a little bit more difficult. 4,300 divided by 14. Yeah, 307.14 watts. Okay. So we found our P out. Now we have to figure out, okay, what do we put in the system in order to do this? All right. So for the first scenario, I had to take my current times my voltage. So for all three of them, we used 110 volts, but it's the amount of current that it drew was a little bit different. So for my P in, I'm going to take 1.1 and multiply that by 110 volts. I'm going to take 1.8 and multiply that by 110 volts. And I'm going to take, error here, 4.8 and multiply that by 110 volts. Kind of squishing here, I apologize. For the first one, you should have got, or you should have got an answer of 121 watts. For the second one, 198 watts. And then for the third one, 528 watts. Okay? What's left? The efficiency part, right? We know what we put into it. We know what we got out of it. Now we just have to divide the two to figure out how efficient the system was. So I will put that on a separate piece of paper so we can clean things up a little bit. So for one, the P out was 100 and the P in was 121. For number two, the P out was 180 and the P in was 198. And for number three, we had 307.14 out and 528 in. What do you notice about these three answers that we have here, three formulas that were set up here? When we figure this out for all three of these, they're all going to be less than what? Well, less than 1, right? And if we multiply by 100 for percentage, it'd be less than 100%, right? So, and you know that right off the bat because the number on the bottom is larger than the number on the top, so it's going to be less than 100%. And going back to our law of conservation of energy, we can't create or destroy. We can't have more than 100% efficient system, okay? In fact, we can't even have a 100% efficient system. We're always losing energy somehow through conversions. All right, so for the first one, you should have gotten an answer once you multiply by 100 of 82.6%-ish. For the second one, 91%. And for the third one, 58.2%. And again, depending on rounding and how many numbers you carry, somewhere in that neighborhood. So right off the bat, which one's more efficient? Number two is the one that's more efficient. It was the most efficient system. Okay? So on the quiz, or maybe even on the final at the end of the year, you might see something like this. So I want to make sure you're aware of how to solve it. You already know how to solve it. Sometimes it's just the way it's positioned that you forget what it's asking for. Okay?